So we have that sigma I is just sigma I 1 over 2 times sigma I 1 over 2. Okay. Well, actually, that one's symmetrical, so I don't even need to transpose it. Okay. And we're going to call this whole thing constraint 1. Like this entire thing is 1. Okay. And finally, by using this instead of this probabilistic constraint, we get the final version of our SOCP. Okay, so SOCP for uncertainty. Okay, we have minimize over W B epsilon 1 over 2 W square plus C from sigma I. Okay, and this is subject to 1. And epsilon greater than 0. Okay? All right. As I said, the paper also provides a similar SOCP for the case when xi is normally distributed. And the constraints are tighter because we actually know the distribution for that case. Let me see. Okay, so we've only got, yeah.
By missing data, you mean that the X's are missed?
So in this case, we haven't dealt with missing data. We've just dealt with uncertainty. So the missing data is actually coming, the variant of the SOCP for missing data is actually, I'll present that right now. This is just for uncertainty. That is, you don't have a sample xi, you just have a distribution over your samples.
We have uncertainty on X, not Y.
Yes, the Y is fixed. That one we know is correct. Okay. Okay. And there is a geometric interpretation of this constraint. And actually, so this constraint corresponds to an ellipsoid. And basically, the requirement is that inside the ellipsoid, you classify correctly. Okay, so I don't really think I have time to go into that. But maybe I have time to write. So there's a category of SVMs called SVMs with set constraints. With set constraints. And the constraints look like this. So they just look like the standard SVM constraint, except this needs to hold only for X in some set. Okay? And depending on the set, so for if the set is just so depending on SI. So this can be just the samples that we have, in which case this is just standard SVM. Okay, it could, and the optimization problem for this is a QP. Okay, it could be a polyhedron. In which case we get a QP, and this is something called knowledge-based SVM. Okay, and we also get a QP here. There's also we can consider here the trajectory of a polynomial. And in this case, we get something like an invariant SVM. So an SVM that's invariant to scale or rotation. And it's just kind of a polynomial. It's kind of a spectrohedron. It's just like it's just a condition on a polynomial on your x's. Do you guys follow? Well, in any case, for that one, we get an SDP as opposed to an SOCP or a QP. So this is slightly more difficult, as you would imagine, because the constraint is the constraint is higher order. So it'll be more difficult. And this is a paper by Greipel and Hebrich. This was ICML 2004. I think no, sorry, not ICML. I think it was JMLR 2004. Anyway, 2004. They did this stuff. Okay. If it's an ellipsoid, then we get back that constraint, and it's basically this paper, and we showed its SOCP. And okay, I guess that's about it. So that's kind of a list of SVM variants and the complexities of their corresponding optimization programs. Yeah. So basically here, you require that you classify correctly within a convex set only, right? In the ordinary SVM, you just require that you classify correctly over the samples.
Yeah.
In here, your requirement is more stringent in that you want to classify correctly over an entire ellipsoid, over an entire set.
Do you guys still remember when I covered the robust optimization, stochastic optimization? This derivation over on your left can be considered from the probabilistic point of view, so it's considered stochastic optimization. On the right, all this is the so-called uncertainty set. They take different geometric shape, and we need all the x that within the geometric shape to be covered. So it's like an infinite number of linear FM constraints. So
I'm just interested to know, I mean, if we wanted to use it using an ordinary SVM, for every x in Si, we would have different epsilon I.
you can't do
As
that
you
because
said,
there's
infinite number.
number.
Yeah, infinite number.
Well, it's like you take a soup over all the points.
Oh.
Yeah. Okay. Well, okay. So that deals with uncertainty, and of course we have the second part, which deals with actual missing values. Okay. So we'll have to compute the sample mean and covariance and do EM to kind of estimate our missing values. And let's say we have our sample is X and Y, and let's call XM for missing and XA for available. Then our mu will have two components. Okay. And our sigma will also be decomposable. Okay. So we'll first estimate these. Then we'll try to solve a system of equations to determine the missing values using these two parameters. So we're just going to determine, we're going to imputate the missing values here. And we do that by just writing so we know that the missing values also come from the same distribution as everything else. So, yeah?
Sorry, the paper that you cited there, what's the name? I could not find it there.
So Grapel and Herbrick?
Yeah, Ralph Herbrick and
Yeah, so it should be, you could send me email. I'll retrieve it for you, okay?
Homo Grapel and Ralph.
Yeah.
Yeah, they have.
So it's referenced in this paper by Alex.
Okay.
Okay, so have a look at that. Okay, that's yeah, no worries. Okay, so we're simply writing the conditions on the missing values, knowing that they come from this distribution. Actually, this is, I'd not have had to do this because I think you guys already know how to estimate them. Okay, and after we've done this estimation, we're just gonna compute the mean and the variance again. So we'll just do an iterative procedure until convergence. Okay. Now let's assume that in our samples, so let's assume that samples 1 through C are missing. Are available, complete. And C plus 1 to N have missing values. Okay, then the optimization is similar to what we have over there. So our missing values are actually the uncertain ones. So for the values that we do have, we're just going to use the standard SVM constraint. And for the missing values, we're going to use the constraint that we derived for uncertainty. So let me just show you how it looks like now. So it'll be minimize over the slack variables. Okay, so subject to. And now we have first, for our complete values, just the standard, SVM constraint. Okay. Okay, for our missing values, we'll just have the uncertainty constraint. Okay, notice I'm going to use this xi bar. In this case, xi bar represents all the samples, the missing rows, with so the rows that have incomplete data with the missing values filled in through that procedure. Okay? So these are the automatically completed missing values.
It almost feels like, for the missing values, you are imputing their mean into that, in the missing.
Well, I'm imputing the value we obtained after many iterations of EM. It's not really their mean.
It's x bar I is not the mean of the rest of the.
No. It's something that we got after that procedure. So xi bar represents the ith sample, the completed version of the ith, the automatically completed version of the ith sample.
And
Like through this procedure will give me a way. I can't just call it xi because xi in its natural form has missing. Maybe I should just call it. Let me just call it xi tilde, so you guys know it's not the same as the mean. Okay. So here pretty much everything stays the same. Okay, I here is from C+1.
So I have another question.
Yeah.
So I still don't I'm not able to see how you got excited. I see that you got this mean.
Okay, so I initialize the mean and variance with, the mean over, say, the mean and variance over the observed data, and maybe here with zeros or something like that. Okay. Okay, then I solve this linear system of equations to get xi tilde 0, right? Then I use that xi tilde 0, the xi's, whatever, the i's go from C+1 to n, okay? And recompute mu and sigma. Then I compute the x tilde for the next iteration.
And what's the basis for this? Why would this give
This
us-
convert, it just convert, this is just EM.
Yeah, but like.
It's convex, it'll convert. Okay, Yushan, does that make sense?
It makes sense, but I'm also not convinced that
So it'll converge because it's just a convex optimization.
I can imagine it's converging. Like it makes intuitive sense, but like why would it give me better results compared to just imputing the mean of the values that I like? Generally in data mining, what people do is for missing values, they just compute the mean of the rest of the things and just impute it.
So I see. So they do have error bounds for this. So I'm not going to go because the point of this is just for me to go over the SDP with you guys. So look at the paper. They do compute some error bounds for this. So I'm sure they get something better than if they just put the mean in there. Okay. Generally, if you do several iterations, you get something that's closer to realistic values then. Okay, because you're also using the other values that you have in that vector xi, right? Because you'll have some values will be there. So you're going to use the other features to kind of get your missing features. Okay, so.
we will converge, but I'm not entirely clear that this is actually a convex optimization because we have missing data in there. We need to, so overall, both this W and this XIs are xi tutors, they are like unknown variables. If
Yeah.
we want to jointly optimize over them, this is a
No, but that's well, yeah, overall it might not be convex.
yeah.
It's just every
Each
part.
step you are
Yeah.
going to-
Right, that's EM. You're not gonna, so each part of that is convex. The whole optimization procedure is not convex. Sorry, I didn't mean to confuse you guys over there. Yeah, just you can't get any better. Okay, so here sigma, I haven't really defined, so I told you what x tilde I is. I haven't told you what sigma I is. So it's just, it'll just be something like this. So this corresponds to the constraint that we have over there. Okay. So these we've introduced these gamma i's, and these things control the robustness to the imputed values. Okay. So we can make it more or less likely to change depending on the values that we put in. Okay, and we of course have our let's not forget about our constraint on W. Okay, and yeah, the epsilons, the slack variables. Okay, that's also has a constraint. All right, so okay, I think that's about it for the SOCP that deals with missing and uncertain data. Does everyone get the idea behind this? Okay, so I was planning to do the paper by Lancreate and Bartlett, published at JMLR in 2004, for learning the gram matrix using an SDP. So do you think I have time to, it's about as long as this one. Should I save it for next recitation? Or should we just try to go through it really quickly now?
As long as this one?
Yes. Or longer, probably. So yeah, then let's do that next time. And maybe we'll have time for something else if I plan this better. Okay, well, that's about it for today. Okay, thank you guys for coming.